Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in this video, we are going to discuss about the assumptions of the ARIMA model and how do you test for them. So this is another important interview question which does test a lot of your concepts around time series analysis. And ARIMA is a widely used approach for time series forecasting, and to use an ARIMA model effectively, there are certain assumptions that need to be met. So here are some of the key assumptions and how you can test for them. So the first assumption would be of linearity. So this states that the relationship between your variables should be linear. And when I say variables, what I mean is that the current value, the past value, and the past errors, all the relationships between these three should be linear. And this is what we do in an ARIMA model, right? We use the past values and the past errors to try to forecast the next value in the series, right? So this is the assumption of linearity, quite straightforward. The second most important assumption is of stationarity. So the time series is assumed to be stationary. And what I mean by that is the statistical properties like mean, variance, and autocorrelation should be constant over time. This is a very critical assumption for the AR and MA components of the ARIMA model to be effective. The third one is no autocorrelation in your residuals. So the residuals obtained from your model should be essentially white noise. And what I mean by that is they should have no autocorrelation and follow a normal distribution with a constant mean and a constant variance. The fourth assumption that you need to state is the normality of residuals. This is pretty straightforward. The residuals should be normally distributed. The fifth one and the last one is the homoscedasticity. The residuals that you have obtained should have constant variance over time. So there is a lot of similarity between the assumptions of a ARIMA model and a linear regression model. So that's there. And now the next question is, how do you test for these assumptions? Knowing these assumptions is good. It tells you whether you can apply a ARIMA model to your time series or not. But how do you understand whether each of these assumptions is being met or whether any of them is being violated? So that's where we talk about the second piece, that is testing of these assumptions. The first one is, how do you basically test for the linearity assumption that you have mentioned above? So linearity is pretty straightforward. You try to do a visual analysis, and that way you can know whether your time series is having a linear pattern or not. And if it does have linearity, then the next thing that could be done is you apply transformations like log transform or a square root if the data appears to be non-linear, and that can make your data linear, right? So this was the first assumption that we had, and this is how you can test for linearity. The second one is the stationarity. So again, for stationarity, a very quick check would be to do a visual inspection. Again, might not be very accurate, but what you can look for is constant mean and variance over time. But a more accurate way of doing this is to use hypothesis testing using inferential statistics. And the first test that you can do there is the ADF test, very popular in the industry. That is an augmented Dickey-Fuller test, where your null hypothesis states that time series has a unit root or it is non-stationary, in other words. And typically based on the p-value that you obtain after performing the ADF test, based on a significance level, which is 0.05 typically, but again this could be changed depending on your requirements and depending on the context, but typically 0.05 is the significance level which is considered. So if your p-value is less than your significance level, that is say alpha, so that means that you can reject your null hypothesis, or in other words it means that you can say that there is stationarity in your time series, right? And if you identify that there is stationarity in your time series, then it's well and good. But if the time series is non-stationary, so to make it stationary, what you can do is you can apply differencing, that is subtracting the consecutive observations to achieve the stationarity. And once you have the stationarity, the assumption for the stationarity in the ARIMA model is being met. The third one is no autocorrelation in your residuals. So again, visually you can check it using ACF and PACF, that is autocorrelation function and partial autocorrelation function plots. And significant spikes outside the confidence intervals here would indicate autocorrelation. But again, a more accurate way of doing this is to use something called as a Jung box test. And here your null hypothesis states that your residuals are independently distributed, and a p-value of greater than your significance level, which is again typically considered as 0.05, would mean that you cannot reject your null hypothesis, or in other words, it would mean that there is no autocorrelation, right? So this checks for the third assumption that we have. The fourth one is normality of residuals. Again, this is pretty straightforward. Once you have your residuals, there are two ways of testing for it again. The first one is something called as a QQ plot. That's a visual way of identifying whether your residuals are normally distributed or not. But a more accurate way is again to go via the hypothesis testing route and use a statistical test called the KS test. There are a lot many other tests for testing normality of a particular distribution or a particular input vector or series of data, right? Whatever you want to call it. But KS test is one of the most popular ones, and the null hypothesis in the KS test says that the residuals are drawn from a normal distribution, and a p-value less than your significance level means that you can reject the null hypothesis, or in other words, you can say that the residuals are not normally distributed, right? The last assumption is of homoscedasticity. The simplest way to do it is to do a visual inspection, plot your residuals against the time and check for the constant spread. And that way you can understand whether you have homoscedasticity or not. And again, the better way to do it is to go via the hypothesis testing route. So there's another test called Breusch-Pagan test. And here the null hypothesis indicates homoscedasticity and a p-value greater than the significance level. That means you cannot reject your null hypothesis, or which indirectly means that yes, the assumption for homoscedasticity is also met. So you don't need to worry about a lot of these tests. So you can use packages in Python like stats models to test for these very easily in very few lines of code. Not more than a couple of lines of code. You can obtain the p-value, and then basis the p-value and the significance level, you can make a call whether some of these assumptions are being met or not. But it's really important to understand all of these, because understanding these assumptions and testing for them before applying ARIMA is crucial for effective time series forecasting. ARIMA, while being a plain vanilla model, serves as an excellent starting point for many of the time series problems. Its simplicity makes it a great benchmark for comparing this with more complex models that you might develop down the lane. But remember, in a data science interview, a deep grasp of these concepts is essential. The interviewers will expect you not only to apply ARIMA effectively, but also demonstrate a thorough understanding of its underlying assumptions and diagnostic tests. Mastering these aspects will showcase your depth of knowledge and readiness for the real world data challenges. I hope this video helped you, and if you are sticking till the end, then thank you so much for watching. And I hope that this has provided you with a solid foundation to excel in your time series forecasting endeavors and interviews. So if it did, please consider liking this particular video and subscribing to this particular channel, because I plan on uploading more such content around different data science topics. The data science is a vast ocean and there are lots of things to cover, and specifically when you go for an interview, it's important to understand all of these things theoretically, because the depth of your knowledge is at test when you're interviewing for a data science role, right? So hopefully this video helped you, and I will see you in the next video. Then until then, take care, bye bye, and see you.